So we'll go ahead and start. So just a reminder that if you did not, please scan and send that work from exam 1 so I can get partial credit. This week your first due date's on Wednesday. That's the third, sections 3.1 and 3.2. Both of those are in MyLab Math. So we're going to go ahead and get started in section 3.1. It's a fairly beefy section. There's a lot of material in it. So it's a lot of little pieces coming together. So chapter 3 in general is all about functions. And once we start chapter 3 and define what a function is, we're going to be in this function world for the rest of the semester. So section 3.1 is just an introduction. So far what we've been dealing with our equations are basically relations. So the equations we've been working with, or we've seen, are called relations. And what a relation is it's basically just a correspondence between two sets. And when we talk about these two sets, what we're really talking about in terms of algebra is a set of x values and a set of y values. So it's a correspondence between x's and y's. And that's why when we went to find intercepts, we could plug in a 0 for one of those variables and find the other, is because there was a relationship between the x's and the y's. So today specifically, we're going to talk about a specific type of relation. So now we will look at a specific type of relation, and that's called a function. So from here on in, the types of relations we're going to deal with are called functions. And I think you probably have seen this before. I'm going to give you a layman's definition of a function. So we're going to come in and define it. It's one of the few things where we definitely are specific about that definition. So we're going to define a function. And basically for us, it says basically that a function relates two sets in a specific fashion. Each element of the first set corresponds to one element in the second set. So for each element in that first set, an element here means a number or a variable. In that first set, there's only one element that it corresponds to in the second set. So when you give one input, you get one output. And that's really what I need you to remember more than anything else. So this means that one input gives one output. So when I put a number into a function, I'm going to get out of it just a single number. So one in, one out. And that defines a function for us. Okay, have you heard of that before? Does that ring a bell with everybody somewhat? I know that.
Knew it is for one x, there's always one y.
That's exactly it. So right now we're going to come back in and put those x's and y's on there. So is everybody good? I can erase?
Yep, I'm good.
Okay. So yeah, so So the set of inputs is called the domain. So the set of inputs is the domain and represents the x values, yeah. And is our x values. So the inputs are the x values. We call that set of them the domain. And does anybody remember what the set of outputs is called?
Range.
Good job. Set of outputs is called the range. And is our y values. Yep, that's exactly it. So to make sure the idea of one input and one output makes sense in your brain, what we do are we call function pictures more than anything else. So what we're going to do is just draw some weird looking circles. And we're going to let the first circle be our set of inputs. And again, this would be the x values, also known as the domain. And the second blob is going to be our output, which is our y values, which is our range. And so for a function, it simply says that if you have a number in that first set, it's going to correspond to one number in the second set. So one input gives me one output. Each input gives a single output. And so you'll see these pictures in the text. If you go looking in the text, you'll see them. So that relationship is specifically defined as a function. So again, we're taking all the equations that you deal with in mathematics and we're defining them as either a function or not a function. This one's a function. So this represents a function. Now what we're going to do is we're going to draw another picture, and I want to know whether or not it is also a function. So we're going to use the same idea of two blobs. And this would be your input. This is your output. So the first set's got two elements in it. It's hard to make my blobs look good on the board here. And the second set's got two elements or numbers in it. So I want to know whether or not this represents a function. So does the one input give one output work for this picture? What do you think?
No.
And you are correct. So this is not a function. And the reason is this guy right here corresponds to two outputs. So if I label this as like B, B corresponds to two outputs. So I can't have two things that it corresponds to. One input, one output. Okay, we're gonna do one more. I'm trying to make sure my picture's on the board. So again, here's our inputs. And you'll notice that when I do this, I've been doing it left to right. That's to lay the groundwork for how we write functions from left to right. So this time, we're gonna do this. I'm gonna have two numbers in my first set. I'm gonna have only a single number in the second set. And the question is whether or not that represents a function. So does it follow the path of one input, one output?
Yeah.
Yes. Good job. So this one is yes, it's a function. So each input corresponds to one output. It doesn't matter that they correspond to the same output. That's not part of our definition. Just one input, one output. Good. Comments or questions so far?
Makes sense.
Okay, so then the homework starts off with a couple of things like this, where they basically are listing things in sets and asking whether or not it's a function. And then the next thing they're going to ask you to do is determine whether or not an equation represents a function. So this ties into the work we've already done. So I want to determine whether the equation is a function. So we're going to start off with y plus 2x equals 5. So we know that that's a linear equation from the stuff that we saw in the previous chapter or work. Okay, so to answer this question, we have to get to that definition. So the first thing I want you to do is ask yourself a couple of questions. So the first question to ask yourself, Q for question, is can you isolate y? So in other words, can you get the y by itself? Well, in this case, that's a definite yes, because all I have to do is move the 2x over and I would have the y by itself. So y minus y equals, let me try that again, 5 minus 2x. So that's a yes. So in this case, we're going to say yes. The second question is, now, if you give one input, do you get one output? So if you plug in one value, you get one value out. So if you plug in one number, do you get one number out? And that's the second thing you have to ask yourself. So in this case, we can just sit here and plug in different numbers. If I plug in a 0, I'm only going to get one number out. If I plug in a 5, I'm only going to get one number out. If I plug in a -2, I'm only going to get one number out. So the answer to this question would also be yes. And if both answers are yes, then it's a function. So this is a function. And in this case, it's a linear function because all the exponents are positive ones. So okay, that was a pretty easy and straightforward example. So let's do one that's a little bit uglier. Okay. So if you can isolate the y, that's the first step. And if you can plug in one value and get out one value, then we know it's a function. But in order to see this input-output, that's why you isolate the y first. Let's try another one. So I'm going to pick off of what we did in the last chapter. I'm going to look at a circle. So I have x squared plus y squared is equal to 4. So we know that's a circle because both the x and the y are squared. We also know that that circle is centered at the origin because we don't have the h and the k, and it would have a radius of 2. So it's a circle. We recognize it. Okay, let's come in and isolate the y value. So to isolate the y value, I'm going to move my x squared. That'll give me y squared equals 4 minus x squared. And then solving for y, I'm going to come in and square root both sides. And I need to remember that anytime I square root both sides to add on a plus or minus when I'm solving. So I get plus or minus 4 minus x squared. So the answer to the first question is, yeah, I can still isolate the y. I can solve this thing for y and get the y by itself. However, this time, if I plug in one input, such as 0, so if we come in and let x equals 0, then y would be plus or minus the square root of 4, which is plus or minus 2. I get 2 outputs. So it's not a function. And when we come back tomorrow, we'll have a better way of looking at a graph and telling whether or not it's a function, but we don't have that yet. So this is the only way we can do it. Okay, so everybody see that plus or minus is impacting things? And that's why it's not a function. So when you solve for y and you get a plus or minus, you know it's not a function. Okay, any comments or questions about that? So we did talk about the input being from the domain. Just as a comment, sometimes textbooks or the MyLab Math will use the idea that the input is the independent variable and that the output is the dependent variable. that comes from this kind of example. In other words, we could pick an X value. It was independent of anything else. But once we picked our X value and plugged it in, we definitely got a dependent value for our Y's. So Y depends on what you plug in for X. So that's why they're called independent and dependent. So just in case you see those terms on the homework, you'll recognize them. So again, the input is the X, the output is the Y. So for us, our independent variable is X. So mathematicians a long time ago decided, though, if we have this special kind of relation that's called a function, then we probably ought to give it its own notation so that everybody knows that it's different. So we have something called function notation. And again, I think you've seen this. It's just a matter of reminding you. So we just had y was equal to, I think it was 5 minus 2x. So this is written as an equation. It is a function, but it's written as an equation. Well, what we're going to do is we're going to come in and replace y with f of x. So you're going to see an f, and then in parentheses you see an x. So to write this as a function, I would have f of x equals 5 minus 2x. They mean the exact same thing. In terms of working with them, they mean the exact same thing. It's just as talking a slightly different language. So like speaking Latin all of a sudden, we write f of x in place of that y. Still means that you're plugging in x, you're getting out of it a y value or a corresponding output, which we're going to call f of x. The key to writing functions is to recognize that whatever letter you put inside that set of parentheses is going to be the only letter you can have on the right-hand side. So if I write a function in terms of x, the only variable I can have on this right-hand side is x. Okay? And again, how we say this, so it's said f and then the word of x. It does not mean to multiply. Not multiplication. It's the one place in algebra where you see parentheses and it does not mean to multiply. So the first thing we want to do is come in and actually make sure you're comfortable with the notation. So let's go ahead and use this as our example. What I want to do is I want to evaluate f of x at different values. So the first one we're going to do is let's go find f of 4. So notice I've taken the x out of the function notation and replaced it with a 4. So that means that any place I see an x, I'm going to replace it with 4. So this is simply telling me my replacement value. So we're going to come in and we're going to take the 4 and write it in place of that x. So instead of 5 minus 2x, we have now 5 minus 2 times 4. And we're going to go ahead and simplify that. So that would be 5 minus 8, which is going to give me a negative 3. Okay, have you done this before?
Yes.
Yes?
Yes.
Good. Woohoo! And I know Adam and Matt have because they've been through the 101 course with me. So good. Okay, let's get a little bit more complicated because that's a little bit too easy for us. So let's do a function that's a little more ugly. Start dealing with some exponents. So let's say f of x is equal to, and I'm going to do x squared plus 3x minus 2. And then we want to find, and we're going to do quite a few parts here. I apologize, the homework, there's like 10 parts to one problem. It's like, oh my gosh. So for part A, let's come in and find f of 1. So now we're going to come in and replace all those x's with a 1. So that would be a 1 that I have to square plus 3 times 1 minus 2. So 1 squared is 1, 3 times 1 is 3, minus 2. So 1 plus 3 is 4, minus 2 gives me 2. So 1 input, 1 output. The x value is 1, the y value is 2. So it really is a point on a graph, or it will be tomorrow. And let's plug in a negative number. So this time let's plug in a negative 1. So how about f of negative 1? So that would be negative 1 squared plus 3 times negative 1 minus 2. So again, any place I see the x, I'm going to replace it with my negative 1. So negative 1 squared plus 3 times the negative 1 minus that 2. Okay, now be really careful here. So -1 squared is a +1. +3 times -1 is a -3, and then I'll have a -2. So I end up with 1 minus 5, which is a -4. One input, one output, just like we're expecting. Okay, part C, let's go and plug in f of a. So instead of plugging in a number, they want me to plug in a letter. So in place of all those x's, we're going to plug in an a. So I would have an a squared plus 3 times the a minus 2. And I can't do anything else with that, so I leave it alone. So this time the input was a, the output is an expression, and that's okay also. There's nothing wrong with that. Everybody doing okay so far? Okay, what if I ask for a negative f of x? So notice I'm not doing anything to the function itself. I'm not replacing the x at all. What this is asking me to do is to take the opposite of that function. So what I like to do is put a negative in front, and then I'm going to rewrite the function. And then I can distribute the negative in. So when I distribute the negative in, it'll make it a negative x squared. I'll take a negative of that positive 3x, making that a minus 3x. And then I'll have a plus 2 because that negative makes that a positive 2. So again, I input, in this case, just the x, and then I take the opposite of the entire thing. And you're saying, why the heck would I want to do that? Well, let's do one more. Let's do f of negative x. So wait a minute, we did this when we talked about symmetry. We replaced x with a negative x, so we've seen this idea before. So now I'm going to go back to my original function. I'm going to replace all those x's with negatives. So I have a negative x in parentheses that I need to square. I'm going to have 3 times the negative x and then minus 2. Well, we know a negative x squared is a positive x squared. And again, notice the exponent stays there. That positive 3 times that negative x is going to make that a minus 3x. And that minus 2 is going to stay as a minus 2. Okay, now moving forward, what we're going to do is go back to the idea of symmetry and plugging in a negative x and having the opposite. So we'll use both D and E moving forward to talk about symmetry in terms of functions. So we just need the ability to plug in and get stuff out of it. And then finally, just one more. Let's come in and do f of x plus 1. So now we're going to come in and replace x with an x plus 1 in every single spot. So back to our original again. We'll have an x plus 1, which we're going to square, plus 3 times the x plus 1 minus 2. And of course, we're not done with that. We need to clean that up. So right underneath this, I'm going to write what x plus 1 squared means. It means x plus 1 times x plus 1. So let's go ahead and FOIL that out. So we'll get an x squared. The outside term is going to give me a 1x, and so will the inside term. So that's going to give me a 2x. And then the 1 times the 1 is going to give me a 1. Now I'm going to distribute my 3. So I'll have plus 3x plus 3. And then I have a minus 2 at the end of it. A minus 2. And now we can collect like terms and call it good. So I'll have x squared. I have a 2x and a 3x. That's going to give me 5x. A 1 plus a 3 minus 2. So that's 4 minus 2, which is positive 2. So when it's all said and done, I end up with x squared plus 5x plus 2. So I plugged in an expression, and I get out of it an expression, which is what we're expecting. So, but again, one input still only gave me one output. And believe it or not, what we're doing right here is laying groundwork for your calculus courses. So some of you will move on and take the applied calc. Some of you will move on and take the theoretical calc. But in both cases, this function notation of plugging in an expression and getting out of an expression is laying groundwork. So, okay, anything causing questions right now?
Can you do a D and E again, please?
Yes. So I'm going to erase part F. Okay. Let's go through D again, and then I'll come back in and rewrite E. So what D is asking us to do is to take the opposite of the function. So this means the opposite of f of x. So it's not changing anything on the inside of the function. It's simply asking me to take the opposite of it. So I put a negative in front of the entire function, and then all I'm going to do is distribute it in. So it's going to make that first term a negative, it's going to make the next term a negative, and it's going to make the last term a positive. So it simply changes the sign on each term, because that's all they're asking me to do. So just like finding the opposite of a number is just changing its sign. We change the sign on all the terms. For part E, they're asking me to come in and replace x with a negative x. So I'm going to go back to my original. Every time, go back to the original. In any place I have an x, I'm going to write a negative x. So in place of that x, we wrote a negative x, which we had to square. In place of the next one, we wrote a negative x, and then the minus 2. So now we're going to clean that up. A negative number squared becomes a positive number. So all I'm really doing when I square this is dropping it. You're taking negative x times negative x. That's a positive x squared. The positive 3 times that negative x is going to make that into a minus 3x. And then the 2 we didn't touch, so it comes along as a negative 2. So and again, where we're headed in just like 1 or 2 sections is we're going to compare these two answers together, and it's going to tell us something about the symmetry of the function. So that's why we need it in our course. Okay, does that help?
Yes, thank you.
Well, and you have to do quite a few of these. So I think you have like 2 that have got like 10 parts to them, and it's just the practice. You just need practice. You cannot speak a foreign language unless you practice the foreign language. So that's what math is, a foreign language for all of us. Okay, the next thing we're going to do is we're going to combine functions together. So combining functions. So I've been kind of specific. We're going to start off with a function f of x is equal, let's do just x plus 3. So that's going to be a linear function for us in the future because we know that all the x's have first degrees on them, so it's a linear function. This time I'm going to give you another function. So we're going to say, and g of x is equal to x squared minus 2x. Okay, how do I know the second one's a function? By its notation alone, because they gave me a variable, f, g, h, doesn't matter what letter, but in parentheses I've got an x. So I again know that this is a function. It's just written in terms of g. I can literally use any letter I want outside the parentheses. I can use an s, I can use an r. We will use lots of different letters. So I have 2 different functions. We know the first one's a line. The second one we know is a quadratic because we dealt with quadratics in the previous chapter, chapter 1. So. Okay, what we want to do is we want to combine them. So the first thing we want to do is find, we're going to do f plus g of x. Now that's new notation. F plus g of x. What the heck does that mean? Well, it simply means that we're going to take f of x and add it to g of x. In other words, if you have 2 functions, you can add them together. Well, we can do that. We can come in and replace f of x with x plus 3, and then add g of x, which is x squared minus 2x. So I'm simply taking my 2 functions, putting a plus between them, and adding them together. So then let's collect like terms and put it in descending order. I'll have an x squared. The x minus the 2x is going to give me a minus x plus 3, and then I'm done. That's it. I don't have to do anything else to it. Now, why would you ever need to add functions together? So let me try and give you some background on it. So in other words, if you have a strange shaped window in your house. So this is called a Norman window. It's a window that's got an arch on the top of it. And if one function represents, it's not these 2 functions, but one function represents the area of this rectangular part, and another function represents the area of the semicircle part, in order to find the area total, couldn't you add those functions together? So that's why we need to be able to manipulate functions, because we're going to be adding them together in our future. So then what we could also do is once I've added them together, could I come in and evaluate it at a value? So can I find f plus g of 0? Well, yeah. Can't I just plug 0 in? to the addition of the two functions. So I'm going to take the answer I just got, and I'm going to plug in a 0. So I'm going to have a 0 squared minus a 0 plus 3. Well, that's 0. That's 0. I end up with 3. So I'm going to add two functions, and then I can evaluate those functions. Any comments or questions? Okay. Okay, I'd like to note that in this example, right, what if I found f of 0? So what if I did not add the functions together? What if I want to be more efficient and just plug f of 0? So I'm going to take 0, plug it into the f function. So that would be 0 plus 3, which is 3. I'm going to take that same input, the 0, and plug it into the g function. So that would be 0 squared minus 2 times 0. Well, that's just 0. So now what happens if I take f of 0 and g of 0 and add them together? So in other words, what if I add those two outputs together? I get 3 plus 0, which is 3. Notice I get the same answer. Okay, so what's the moral of this story? Well, the moral of the story is you can add the functions together algebraically and then plug in your value, or you can plug in the value and then add the answers together. It doesn't matter in what order you do it, and that's the beauty of functions in terms of the combining it. Any comments or questions? This was easier to do because we'd already added them together, but if I didn't actually have to add them together, I would just plug the numbers in. If I were given a number, what's the difference? Whether or not I'm giving an x or whether I'm given a value. So if I'm giving an x, I'm going to have to add them together. If I'm given just a number, I'm going to plug it in and then add them. So, okay, well, if I can add functions, what else do you think we can do? After addition, they usually teach you to subtract. So we could do f minus g. So that would be f of x minus g of x. Be really careful here because you're likely to make some sloppy mistakes. So I'm going to take my first function, which is f, and then I'm going to subtract the second function. And when I do a subtraction of a function, I tend to put it in parentheses so that I remember to change the signs as I'm subtracting them. So you'll notice I put a minus here. So that's going to make that x plus 3 and a negative x squared, but a positive 2x. So don't forget to switch your signs. Be careful. Then we'll collect like terms. So we have a negative x squared. This time when I add the x's, I'll get a 3x plus 3. So when I subtract the two functions, I get something vastly different. I get a negative x squared, a positive 3x, and a plus 3. Well, if I can add and subtract, then we can also multiply. So we can do f times g of x. Okay. And I'll put a little dot there just so you know this simply means f of x times g of x. Sometimes, depending on the textbook or depending upon the professor, you'll actually write this as fg of x with no symbol between the f and the g, because we know when two things are next to each other, it means to multiply. So it means the same thing. We'll go ahead and do that really quick. So we're going to take x plus 3 and multiply it by x squared minus 2x. I'm simply taking my two functions and multiplying them together. Okay, so if we do this, we'll need to go ahead and clean this up. So we'll FOIL them out. So x times x squared is going to give me x to the third. The outside term would be x times that negative 2x, which is a negative 2x squared. 3 times the x squared is going to give me a positive 3x squared. And the positive 3 times the negative 2x is a negative 6x. So I did my first, my outside, my inside, and my last. Collecting like terms, I get x cubed plus x squared minus 6x. So now I've multiplied two functions together. And then you can obviously see where we're headed. We added, we subtracted. So we did a sum, we did a difference. We multiplied, which is a product. So you can also do a quotient or a division. So we would have f divided by g. So notice I put a slash between like a fraction bar. So that really does mean f of x divided by g of x. Recognize here that g of x can't equal 0 because then we'd be dividing by 0. So when you look in the textbook or at any notes, you'll see that that appears. So for us, f divided by g of x simply means to take our f function and put it over our g function. So we end up with x plus 3 over x squared minus 2x. And you're done. So, and again, on some of these problems in the homework, they'll have you plug a number in. So it's your choice. You can either plug the number in and then do the arithmetic, or you can do the algebra of the functions by combining them and then plug the number in. Comments or questions about that? Okay, one more topic and we're done. I knew this was going to be a long lecture. Sorry. Are we good?
Yes.
We won't use it too much, but we will use it here and there to add functions together mostly. Sometimes we'll subtract. Okay, the last thing that you'll need for the homework and to move forward from here is how to find the domains of functions. So we're going to talk about finding the domains of functions. Since our whole definition depends on plugging a number in to get a number out, it's important we know what kinds of numbers we can plug in. So for us right now, we'll have to change this later. We have 3 main types of functions. The 3 types of functions. And again, this will change once we move into our logarithms. This conversation changes. The 3 types of functions. So the order we do them in doesn't matter. I just like to do the easier ones first. So the very first thing we're going to do are the radical equations. Radical equations. And what I specifically mean here is even roots. So, and just to make sure you're comfortable with other notation, I'm going to use h of x this time, not an f or a g, but an h of x. We're going to do the square root of x plus 3. So that is an even root. It's a square root. What we have to worry about is we cannot take the square root of negative numbers because we end up in the I world. We don't want imaginary numbers here at all. So when we have an even root, we have to make sure that the inside stays either as 0 or bigger than 0. So we want to avoid negative numbers. Under the symbol. Now that's only true for even roots. For odd roots, it's okay. So if this were a cube root, we wouldn't have a conversation at all. So we'll do one of those, don't worry. Okay, so what we're going to do is we're going to set the inside greater than or equal to 0. So take whatever's on the inside, set it greater than or equal to 0, because that's going to avoid those negative numbers. So we're going to take x plus 3, set it greater than or equal to 0, and then solve. So we'll move the 3, we get x is greater than or equal to negative 3. So what this is saying is our set of input values are all numbers starting at negative 3 getting bigger. I can check that. So I can plug in negative 3 in because it says it's greater than or equal to. So if I plug in negative 3, I get 0. Square root of 0 is 0. If I plug in 0, because that's bigger than negative 3, I get the square root of 3, which exists. It's a decimal, but it does exist. I can plug in 1. 1 plus 3 is 4. Square root of 4 is 2. So this gives me the set of numbers I can use, but we need to interpret this. So we're going to go to a number line. This is why we did our inequalities that first week of class. We know we need a solid circle because of the equal to on the inequality. And in this case, we need all numbers that are pointing to the right, which is in that direction. So then to answer the question, our domain is going to be starting at negative 3 with a square bracket going off to infinity. So again, this is the set of input values that we can use. So this is the set of input values. So I can't use negative 4 because it's outside the domain. I can't use a negative 10 because it's not inside this set of input values. So again, what the domain gives me is a set of numbers that I can plug in and expect to get numbers back out. We don't know what kind of numbers, but we'll get numbers, and that's the key. Any problem with the radical? We'll do an odd root here in a bit. That's one type. So again, you're just going to take whatever's on the inside, set it greater than or equal to 0, and solve. And I know we do these in 101. The ones you're going to see here are a little more complicated than the ones you did in 101. So just so you know, they might get a little uglier. Okay, the second type are rational functions. You know, that's kind of like a new word for us, rational functions. What that really means is that it's a fraction with x in the denominator. So as far as we're concerned, the word rational simply means it's a fraction, and inside that fraction we see x on the bottom or in the denominator. So as an example, let's go find the domain of h of x equals 2x minus 1 all over, let's do x minus 4. Just to get a negative in. X minus 4. Now again, what the domain is asking me to find is the set of input values. So we want to know what numbers we plug in for x and still get a number back out of it. So the key is one input gives me an output, one output. So that's what it's asking us. So I'm going to play the guessing game. So can I plug in 0? Well, what we really care about is that x in the denominator, because we can't divide by 0. So if I plug in 0, 0 minus 4 is a negative 4. Sure enough, it's a number. I get a negative 1 up top. It's an answer. What number can I not plug in? You guys can answer that. What number can I not use down there?
4.
That's exactly it. And how did you get that?
Because 4 minus 4 equals 0.
Beautiful. So this time what we're going to do is we're going to set the denominator not equal to 0 and solve. So that's a little bit different. We're not used to setting things not equal to, but that's the key here. It can't equal 0. So we're going to take x minus 4 not equal to 0 and just solve it. So we'll move the 4 to the other side. We'll see that x cannot be 4. Beautiful. That was very nice. But you have to interpret that on a number line. So here's the 4. It would be an open circle. You can use everything on the left. You can use everything on the right. You can use everything but 4. So as an answer, using our interval notation, how are we going to write our domain? Well, we can go from negative infinity to 4 with a parenthesis. The parenthesis is what's going to exclude that value of 4 from our answer. And then we're going to go from 4 to infinity. So because we have parentheses around the 4 in both pieces, that's how we're excluding our 4. And this is how we would write it using interval notation. You need to be careful, use whatever the MyLab math is asking you to use. In some places they'll ask for interval notation, in some places they'll ask for basically this kind of notation, just x can't equal 4. Nice. Let's do a little bit more complicated one and then we'll move on. I'm trying to speed up here. Let's do one more of these. So this time our rational function, so I'm going to use r of x for rational function, is x all over x squared minus x minus 6. So x over x squared minus x minus 6. And this just tells you the kind of ugly things that we'll be dealing with as we go through this course. So we're going to do the same thing again. I'm going to take that denominator. I'm going to set it not equal to 0. Okay, and again, the not equal to is not really impacting anything until the end of the question or the problem. So we'll just deal with it. This is a quadratic. Are there factors of 6 that subtract to 1? So factors of 6 that subtract to 1.
3 and 2.
3 and a 2, an x and an x. Because there's a negative on the middle term, we know the 3 is the bigger number and takes the negative. So we'll have an x minus 3 and an x plus 2. Going to set each of those not equal to 0. So we see that x cannot equal 3. And over here, we'll do the same thing with this one. We'll see that x cannot equal a -2. So this time, instead of avoiding just one number in the denominator, we're going to avoid 2 different numbers. If I plug in the 3, that'd be 9 minus 3, which is 6. 6 minus 6 is 0. I cannot divide by 0. So nice. Good job factoring. Now over here, we're going to have our -2. We'll have our 3. We know we cannot use them, so they're going to be open circles. And we can use everything else. So the whole rest of the number line can get used except that -2 and except that 3. So because the graph now is made up of 3 pieces, my domain is going to have a piece that matches each one of those pieces. So on the left, we'll go from -∞ to -2 with a parenthesis. That's excluding it. That's the open circle. We're going to go from -2 to 3. That picks up that middle piece. And then we're going to go from 3 to infinity. So you can use any number you want and plug it in as an input, and you'll get an output that's a real number, except for that -2 and that 3. So the interval notation here is really awkward, but it's concise. It tells us exactly what's going on. Okay. Whew. One more type and we're done. It's our easy type though. So type 3 for now is what I call the anything else. In other words, if I throw anything else at you and ask you for its domain, it really is anything else. So examples might be f of x is equal to 2x plus 5. G of x is equal to x to the 4th power, which we haven't done a lot with, but x to the 4th. H of x is equal to the cubed root of 2x minus 1. Notice it's an odd root. And let's do g of x. No, let's pick up another letter. Q of x. We don't get to use q's very often. So q of x is equal to 1/2 x. Okay. So those are all anything else. So I look at all 4 of those, and what I'm going to note, there's no even radical, and that there's no x in the denominator. So that's what I'm going to note to myself. I don't see a square root or a 4th root or a 6th root, and I see no x in the denominator. I see a fraction, but there's no x on the bottom. So because that is true, then your domain is automatically all real numbers. In other words, you can plug in whatever you want, anything, it doesn't matter, and you will plug in an input and get an output. So there are a couple of ways you can write this. In interval notation, it would be from -∞ to +∞ with parentheses on the ends. So that's another way of writing it. So instead of writing it out in words, you can write it in interval notation. And then there's also a symbol that you can use. It looks like an R with an extra vertical bar on the left-hand side, and that symbol simply means all real numbers in mathematics. So any one of those 3. I have a feeling that MyLab Math's going to use this one quite a bit. Okay, that's your introduction into functions. Any comments or questions about anything that we covered? And it really, really will help for tomorrow's lecture if you go in and try the assignment today sometime. I know it's not due till Wednesday, but in order to move into tomorrow where we're going to analyze graphs of functions, it really helps if you have some background work done on it already. So, anybody have any comments or questions?
No, I'm good.
Okay,
Okay.
enjoy your wonderful day. Have a good one, and we'll see you tomorrow morning. Oh, and make
Thank
sure you send your scratch work from the exam if you didn't. Make sure you get that done so I can grade those, okay?
Okay.
Have a good one. Bye-bye.
Bye.
Bye.